So yeah, last time we were talking about like, well, how would you cross over functions or mathematical expressions? And this is in genetic programming, which will come up shortly. But like if we have the expression 2 pi plus x plus 3 minus y divided by 5 plus 1. Like I was saying last time, I realize this can be simplified, but I'm not going to for the sake of whatever this is. And then I have another expression like a 3 times 3 plus y plus 12. Right? And I say cross those over. Well, yeah, that's kind of a weird thing to say. Like, what does that even mean? Well, if we represent these expressions as these trees, which we call S expressions, symbolic expressions, which is what's typical for genetic programming, crossover becomes just a matter of pick one of the nodes and pick another node, like in the tree, and then exchange them. That's it. And it's all going to be what we call type safe in this example, because everything in here is a number. It could be different if we're dealing with typed genetic programming. More on this in a little bit. But everything in here is a number. Whether either it is literally a number, it is a variable that is effectively a number, or it is an expression that gives me back a number. At the end of the day, every one of these things is going to be evaluated to ultimately a number. So this right here, a times 3, that's going to be of that like a number. Y minus 5 plus 1, that's going to be a number. So I can exchange these things easily. And if I were to, I'd get the trees that look like this. I'm not going to write them out in terms of what they mean, but that's the idea. That's how we could do crossover on an expression like this. And then mutation, this is a bit of a lazy example, I'll admit. Mutation is, well, select an individual node and replace it with some new randomly generated subtree. Now here, the randomly generated subtree, I cheesed it by just saying like, well, it's y, right? Which is valid. But I said, okay, replace this whole subtree with a new subtree I randomly generated that's y. Why is it y? It's random, who cares? So that's how we could do mutation. And if you say, well, how do we randomly generate these trees? Well, we could talk about that a little bit more later, but there's a couple of ways we can go about doing it, right? Really what it'll come down to is how deep do we want the tree? Internal nodes are typically, they have to be operators. Something that takes inputs. It could be a unary, binary, trinary operator. Doesn't really matter. But like here's a binary operator, here's a binary operator, right? So it's going to be some operator. And the leaves are going to be a terminal, whether it's either a literal value or some variable, right? So that's, we just arbitrarily pick, okay, I want a leaf. Okay, pick from the terminal set. You can, yeah, why not? Absolutely. You mean like pick this and exchange it for another operator? Yeah, entirely fine. The issue that could arise here is the same issue that would arise when generating a random tree or crossover is if we have type genetic programming where you have a mix of types where sometimes the subtrees evaluate to a Boolean and other times they evaluate to a number and then maybe it's comparison operators or maybe it's so that could come up, but yeah, absolutely. Absolutely. There's nothing wrong with that. Any other questions about this? We have, at this stage, I just want you to be aware, we haven't really introduced genetic programming yet. At this stage, be aware that genetic programming is one, a thing, and two, it's effectively just a genetic algorithm where we use that as the representation. But we're going to cover this in more detail very soon. Not the next topic, but the next topic. And that's what the next assignment's about, which I moved the deadline back a week, by the way, if you didn't notice. We're moving slow this year for whatever reason, in a good way. Yeah. I think it was originally.
Because I think I was looking at it, so it was 23rd, 28th. Did you move it back to the 28th again?
I moved it to maybe. It may have been. I think what happened before was there was something left over from the previous year, and someone submitted a PR to fix that. I don't remember who it was. It was you. Yeah, you fixed that. Where you're like, why is it talking about updating and complaining about reading week? You're right. That was last year. So there was something there. That may be what you noticed, something from the previous year. But the deadline was like next Monday. And I was like, we won't have it. I have no doubt that y'all will be able to figure out genetic programming before we really sink our teeth into it. But that kind of defeats the purpose of sinking our teeth into it. So I figured, let's push it back a bit. Just no complaining when your project is due and everything, right? Because assignment 3, PSO, will be due, and then your project will be due later. For the project, I'm just going to pause the recording for a second so no one can say anything. All right, we're back, and I didn't say anything incriminating. All right, mutation. All right. So by the way, and genetic programming, which again, we're about to get to, I love genetic programming. I think it's so cool. I think it's so fun. It's effectively using evolutionary algorithms to evolve programs. It's pretty cool. Additional notes. This list is in no way exhaustive. Even if it was, it shouldn't have been, because the point, like I've said before, and I'll keep saying it, none of this stuff with evolutionary computation is intended to be, this is the way you do it. No, it's just inspiration for doing it however the hell you want to do it. These are like common things people talk about, common operators people will use, but that is not to say these are the operators you should use. You are always encouraged to invent your own shit, to try things, to explore things, because that's usually how you'll find what works for your problem, because all of this stuff is too complex to say, you should use this, you should use that. The exception to this rule, I would say, would be with like your floating point stuff, or your permutation representations. Those are pretty common, but anyways. All right, All right. The above give you an idea of what is out there and what works, although you're going to be encouraged to do your own stuff. Not just in this course, but if you do anything with evolutionary computation in general, the idea is you're always just screwing around to see what works. All right, destructive operators. The word destructive was used above when referring to genetic operators. It's not really that well of a defined term, but like I said before, it's kind of this idea of like how destructive something is dependent on the representation and the particular problem. And this is best described with the example like single point crossover on integer representation for a robot navigating a maze. On average, it changes half the chromosome, but the information in the chromosome is preserved and transferred, right? So imagine I had a chromosome that was like move up, up, left, up, left, up, left, I don't know, right? Up, right, down, whatever, right? That's my instruction. If I had another chromosome and I did like a crossover, like if it's a robot navigating a maze, the order really matters, right? The steps and the order in which you take the steps is obviously very important. So one-point crossover is destructive to a degree, but like this chunk is preserved and this chunk is preserved. Presumably, if this was a reasonably good chromosome, this chunk of it might be kind of important that they're together. That contiguous chunk is kind of important. This contiguous chunk is kind of important. And we talked about this yesterday with TSP. When I do the crossover, like an important chunk was preserved. Now, if I did something like n-point crossover, if I crank this up where I didn't do 1 point, but 2 points, or 3 points, 4 points, 5 points, where I always swap alternating bits, and I crank this all the way up to doing something like uniform crossover, that's going to be exceptionally destructive. Every time I do crossover, I'm going to mess up the chromosome so much that any of the goodness that we had in the chromosome is almost certainly destroyed. But this is always, like, don't think, oh, so 1 point crossover is not destructive. No. It would be less destructive on this particular problem with this particular representation. It always depends. So I cannot give you a general rule because there isn't one. It always depends on what you're doing, what the problem is, how you've encoded it. It always depends. People will use these words as absolute, destructive, non-destructive. You should not ever do that. That is wrong. I go to conferences and I hear people talk about this all the time, and I think those people should be ridiculed because it's always a scale. As I just showed you, I can crank up n, and it gets, in this context, it gets more and more and more destructive. And here's another example. And I know I've said this before, but I'm going to re-emphasize it over and over again. Exploration versus exploitation. These are terms people use as absolute terms, when in reality, it's always a lot more fuzzy and gray. So consider the following population for genetic algorithm maximizing the integer value with a single point crossover. We saw this example before. I'm just showing it to you again. Here's my population. It's got 5 elements in it, 1, 2, 3, 4, 5, 5 chromosomes, and they all have some meaning, right? We all know that what I really want is all ones. With crossover alone, well, actually I have to be careful here. If I were to do something like single point crossover, and I were to apply it to this population a bajillion times, it's never possible for me to get the optimal solution. I can't do it. I could exploit what's always good. I could do crossover, and after a long enough time, the population will converge on probably 10111. All of the population will probably become 10111 by virtue of crossover alone, because we're exploiting what's good. 10111 is better than 00010 and 10001 and 00111. It's better, so we can exploit what's good. We can exploit what we already have that's good. But I can never, with single point crossover alone, ever get a 1 at index 1. I can't. That's why something like mutation would be important. And mutation in this context adds the ability to be a little bit more explorative in the search space. So we're exploiting an area of the search space that's good, the 10111. We're moving towards that. Basically, I've got my landscape that looks like this in an idealized situation. Over right here, the local optimum is 10111. But the optimum is over here, 11111. My population will float around here. It's exploiting this area, which is good. But mutation is going to be what can knock a member of the population over here, and then suddenly, hey, there we go. It added the ability to be explorative. Now, to say, well, mutation therefore is more explorative. No. In this context, if we were doing single point mutation, yeah, sure, fine. But these words are used as abstract ideas to describe things in a certain context, not in an absolute general rules way. Okay? I get really mad about this because when other researchers talk about these things in the absolute terms, it's so foolish, it's ridiculous. They shouldn't be allowed to be in the room. Anyways, these just high-level guidelines. Crossover is not always exploitive, nor is mutation always exploitive. A destructive genetic operator is not always exploitive, nor is the less destructive one exploitive. So if we go back to the example over here, if I cranked this up and made it more destructive, you can imagine that we're kind of making the search more explorative by causing the chromosomes, like what they mean, what the encoding means in the phenotype space, it's getting thrown all over the place, right? Something like going from up, up, left, up. If I up, left, up, let me pick a smaller example. Up, left, up, right. And up, right, up, down, down. If I did a crossover like this and got up, down, down, that's going to be more similar to up, left, up, right. Because, well, the first part's like the same. But if they get more and more different, they're getting further away from each other in what they actually mean. So a crossover can be more explorative. This was an example of a destructive one. In the context of this problem, a destructive crossover became more explorative, but it's also, the destructiveness doesn't necessarily mean more explorative either. Just be aware not to use these words in absolutes. Any last questions before we move on to selection and population management? All right. I'm going to open the door. It's getting toasty. These days are crazy when you wake up and it's like 3 degrees and by noon it's like 20. How do you dress?
There was frost on my car this morning and now it's
Dripping in moisture? Yeah. You leave work with a winter coat and you need shorts when you leave work. All right. One of the main driving forces of the computation is the variation operators, and another is the selection. So we have the ability to add variation, but also the ability to select what's good. And taking a step back, we just finished talking about exploration and exploitation. Selection is almost like, well, selection actually lets you exploit what's good. So we could talk about explorative and exploitive in the context of genetic operators, but also in the context of selection and the variation operators. The variation operators are adding variation, therefore they are like intrinsically explorative. And selection, well, we're always selecting what's good, so we want to exploit what's already good. So these terms come up in other areas too. So anyways, yeah, another major driving force is the selection strategy. How do we say who survives and who dies off based on their fitness values? Selection is based on relative fitness values of the individuals. It doesn't even, like the ones that are more fit doesn't mean they're any good, they just mean that they're less shitty than the other ones. And it works independently from the actual problem and representation. Generational versus steady state. So here's the first thing. We talked about this a little bit before, but I'll say it again. There's two major paradigms for doing like a genetic algorithm. There's generational, which is what I like to do, which I recommend. I think it's simpler, but it's not necessarily better. Where you just say, okay, every generation I replace the whole population with selection, right? Where the steady state, what you do is, well, here's what you would do, right? So with generational, you've got your population. You go through, you select until you fill up a whole new population, until it's full. My population, let's say I have 100 individuals in it. So I do selection until I get 100 over here. Then I apply the genetic operators, and I repeat. Steady state, what we do, steady state has like a higher resolution of work, I don't know, for lack of a better term, where you pick the two, you may or may not apply the operators, and then you put them back in the same population. And you do that over and over and over again. They're steady state is arguably a generalization of generational, but I prefer generational. So all algorithms provided have been implemented as a genetic algorithm. The whole population is created, a generational algorithm, pardon me. The whole population is created based on the current population. The new population becomes the current population. The population size remains the same. And there are very discrete gaps in each generation. It's very discrete. With the generational algorithm, depending on how the genetic operators are applied, the new population is filled with copies of unchanged selected chromosomes, mutated selected chromosomes, and offspring resulting from crossover on selected chromosomes, and sometimes both, right? Like where you've got ones that were crossover and mutated, of course. Steady state, on the other hand, has a more continuous form of evolution. And it's not really as clear where the transition from one generation to the next is. In fact, there really is no such idea. With a steady state, given a population size of mu, don't ask me who chose the fancy letters for these. I didn't. Someone at some point did. I don't think they have a meaning. Given a single population of size mu, select some number of chromosomes lambda and apply the variation operators to produce the offspring. Replace the lambda chromosomes in the population with the offspring. So for example, I pick 2, I applied the variation operators, and I have to put them back in the population. But where? Pause. It is possible, and people do this, to have populations that grow and shrink in size. So if I have a population of 100, I pick 2, they mate, and I add 2, I now have a population of size 102. Every once in a while, you're going to need a culling to, shrink that population down. Or usually what people do is they have a fixed size. And so I have these 2, I have to put them back in the population, but I don't have room. I need to make room. So who's going to go? I need to have another selection mechanism. Because I select who I want to mate, and then I have to select who dies off. We're going to talk about examples of this, but common things are well, you just replace the 2 you picked. Some are, no, you leave those 2, and you just pick the 2 with the shittiest fitness. Other ones are replace the ones that are the oldest, that have been in the population the longest without changing. But that requires extra bookkeeping. Replace those that have the least diversity. There's a whole bunch of things you could do. But that's the idea. Now, what they'll call the generational gap is the proportion of the population that was replaced, lambda divided by mu. If the number of chromosomes selected is equal to the population size, it is equivalent to a generational algorithm. If lambda is equal to u, then lambda over lambda is 1. That's a generational gap of 1 that's a generational algorithm. As lambda gets smaller and smaller and smaller and smaller and smaller, then, we're getting a higher and higher and higher resolution, for lack of a better term. Okay. But with the generational gap less than 1, there needs to be another selection mechanism for replacement. Determine which candidate solutions of the population are to be replaced with the lambda offspring. All right? Now, we're going to go talk about regular selection. This is not the I'm going to replace, who's going to die off, whom I'm replacing. No, this is back to selection of who gets selected for mating. Tournament selection. We've talked about this. We've used this before. There are 2 very basic implementations. Uniform selection. Each chromosome has an equal chance of being selected, where the probability of I, where I is some candidate, I guess, so where P of I is the probability of an individual chromosome being selected, well, that's going to be 1 over mu, where mu is the population size. They all have an even likelihood of being selected, okay? It's a uniform probability. Some forms of evolution computation use this selection exclusively. Yeah, there are some forms of evolutionary computation, like specific types of algorithms. I want to say differential evolution does this, but I could be wrong. I can't quite remember, but there are some forms of evolutionary algorithm where they're really, this is not something you tune. Like you pick your selection, this is the selection you use. In general, it's not going to perform well as there's nothing guiding the search. Nothing with this selection strategy like guides the search towards something that's good, right? I just randomly pick one chromosome and put it over here. I randomly pick another chromosome, put it over here. Let's think generational, right? Where I have a population size of 100, I need to select 100 to move it to the next generation. I randomly select 100 and put them over here. Nothing is guiding the search. I'm equally likely to pick a good one as I am to pick a shitty one. So there's nothing really going on there. So yeah, the algorithm will not converge, and this is a case of like something that we would call a situation with very low selection pressure. A high selection pressure is something where the search wants to move towards what's good. A low selection pressure is where, well, it doesn't have a high propensity to do that. The second strategy is select the top chromosomes and only apply the genetic operators. So I always go pick the top chromosomes and then apply the genetic operators. We've already seen this. We've played around with this when we were tinkering, where you always pick the best candidate solutions, but this is not going to work well at all. It's going to converge way too fast. We'll get a situation of that silly little example, that contrived example, where it's impossible for me to get the best candidate solution unless we have something like mutation. But if I'm always picking the best candidate solutions, the population will converge too fast. I will have no diversity in the population, which kills your population's ability to explore the search space. You don't want to do this. So randomly selecting chromosomes to get to the next generation is not very good. And always picking the best ones to go to the next generation is not very good either. And we have seen this empirically. And if you haven't, then you must have missed that lecture where we were dicking around with this stuff. So what do? Well, we want to find somewhere in between. This is way too high selection pressure. Way too high. It's going to converge way too quickly. It's going to like burn out way too fast. So what do we want to do? We want to find somewhere in between. And it's the somewhere in between, this is like tournament selection, and it works really well, actually, in practice. This is what makes tournament selection so good, is it's simple to implement, it's easy to understand, it gives us an easy dial. The dial we'll call K. I think we call it K. K, yeah. It gives us a dial that we can tune to raise and lower the selection pressure very easily. And it's not fitness proportional, but you'll see what that means in a moment. So an alternative, highly effective selection is to go somewhere in between. This is where tournament selection comes in. Randomly pick a subset K, and then select the best of those K. So instead of saying, randomly pick one, put it over here. Or instead of saying, always take the best one and put it over here. What I do is I pick some subset. I pick a few. And then I take the best one of that subset I picked and put it over here. It's not going to be the best one. Maybe it is. It's not going to be the worst one. It's very unlikely. It's always going to be, relatively good to that subset. And this gives us a really good way to control the diversity and like the selection pressure. Think about it. If K is if K is 1, I go to this population and pick 1 and put it over here. Well, that's uniform selection. If K is mu, where mu is the population size, that is always pick the best. Tournament selection allows us to control for k somewhere between 1 and mu. The closer we make k to mu, am I doing this backwards? Yes. The closer we make k to mu, the higher selection pressure we have. The closer we make it to 1, the lower selection pressure we have. So it gives us the control. We don't want a very high selection pressure. We don't want a very low selection pressure. Funnily enough, you want to know what a really damn good K is? 2. 2 tournament. Not 1, 2. It works really well. 3 works really well too. 4 will work really well too. But if you have a population size of like 100 and you're picking only 2, you might be like, that's well off mu. Yeah. And we actually want a very low selection pressure. You do not want your algorithms to converge too quickly. Obviously, these are tunable parameters in certain problems, in certain situations, in certain instances. Maybe you do want k to be really high. But typically, you don't, because you want your population to have a lot of diversity. Yeah?
Having done this for a while, have you noticed a correlation between the size of the project and when it should converge? Because I know that there's not like a should, because there's no should. But like,
You know what? I've never really thought of that question like this before, but I suppose I do. But I don't know how to describe it. I'm going to ask his question. So his question is, having been doing this for years, do I have a sense of, like, well, how long should it take to converge? And my knee-jerk reaction was no, because there is no answer to that question. There really is no answer to that question. But at the end of the day, I totally do. Because if I plot a learning curve and it looks like this, for most problems, I'm going to go, selection pressure is too high. I really should try to do something to fix that. It may be the case where like, that's it. It could be. But my intuition is no. But the funny thing is, I can't give you any numbers because I don't know. I kind of just have a feel for it. I've never thought about it before, but I totally do have like this like sixth sense about like, that doesn't look right. That's a funny question. So I wish I could give you a better answer other than like, I totally have a feel for it, but I don't know what it is. You'll get it after about 10 years, I guess. And of course, everything's tunable, right? So when I get something that doesn't look right, with the experience, you kind of know the usual suspects on like, okay, when the curve looks like this, let's make the population bigger, right? If the curve looks like this is an easy one. What should I do? Run it more generations, right? It could probably keep going, right? If the curve looks, I don't want to get too much in the weeds right now, but like, yeah, there's kind of like the usual suspects on like what to do, but the only way to learn this is to get like a feel for it, like how to ride a bike. I can't describe how to ride a bike other than you just got to kind of do it, right, and figure it out. Yeah. That's a fun question that I never came to terms with the fact that, yeah, I don't know how to describe it. You just kind of know. But yeah, here's tournament selection. Here's an example where K is 3. I pick these 3 chromosomes, 1, 2, 3. They have a fitness value of 2, 2, and 5. This is a maximization problem where bigger is better. So after comparing these two, I take this one A. A was selected. But as you can see in this population, A does not have the best fitness. No. Z's better, W's better, S is better, R is better. So we have a way to include those that aren't as good. But remember, it's important not to think about these algorithms at the start of an evolutionary search. It's important to think, we've been running for 1,000 generations, and we're going to go for another 1,000, let's say. We're letting it run for 2,000 generations. If we're at 1,000 generations in, and I go, well, A is better than X, and better than E, and better than T, kind of ignore these values here. You could just think like some are better and worse than others, right? And I'm saying, you might say like, well, look, the 5, you want like, obviously that's better. Well, first of all, we're going to be doing this over and over and over again, and maybe we have something like elitism to make sure that these are preserved. Fine. But if we're on generation 1000, chances are, like when you look at the curve, it always looks like this, right? And the population will be like around here, right? Where this center line is like the population average fitness, right? Meaning you picked something here, but not the best one. Or maybe something here, but not the best one at any given generation. But the point is, yeah, A is not as good as Z, but A is still good. Like, they're all good. So don't think, oh, I'm picking bad ones. You're only really picking bad ones near the start of the evolutionary search when you have like randomly started populations. Yeah, they're all shit. But everything's relative. And something might be relatively not as good as another, but when you think of like the whole population over time, they're still good. And never discount the diversity. A high fitness is good, but a diverse population is also good. Any questions about what I just said there? Okay. All right. The value of k is typically kept low, but can be adjusted as needed. K is 1, that's uniform. K is mu, that would always be select the best. As k increases, so does the selection pressure. Cool. Tournament selection is one of 2 remarkably popular selection strategies. I always rant about none of these things are hard and fast rules. Always pick what you want, play around, explore, try to invent. For better or worse, you're usually almost always, whenever you're looking at these papers, any journal article or anything like this, and you're looking at selection, if they're doing like a general genetic algorithm, you're always going to see like one of 2 selection strategies picked. It's either going to be tournament or roulette wheel. I still encourage you to try to invent your own, but unlike the genetic operators where really people are just screwing around all the time, when it comes to selection, there really are 2 popular ones. Yeah.
How do papers become, like, how do you make a good paper about this versus a bad one?
You-
Isn't it all like kind of arbitrary?
So it really comes down, this is a very good question. I'm really glad you asked this because somebody I was asking about this yesterday after class, and I meant to bring this up at the beginning of class when it comes to like project ideas. There are 2, I want to talk about this not in terms of like a published journal article, but in terms of like what I would want to see from a project. And it's going to be the same idea. For usually what you're going to see is one of 2 styles of papers, or one of 2 styles of projects. One of the styles is going to be, I've got a problem that I think is interesting, and I want to solve it, because there's no really great solution for this problem. I think it's interesting. Previous years, we had people like do like evolving agents to play video games and stuff. Like there were a lot of like really interesting projects in the past, right? So people come up with an interesting problem, and they're like, I want to apply a genetic algorithm to it. And it's not just like, here's a problem, here's a GA. No, it has to be like, here's a problem, and it makes sense to apply like evolutionary algorithm to it, like something that makes sense. Then you implement it, and you kind of explore a little bit of like some of the genetic operators, you explore selection, you explore all these different values, you try a couple of different things, and you try to get the best results you can. Maybe other people have solved similar problems, and you try to do a little bit of a comparison to that. You're good to go. So that's a very like problem-driven project. Where you find a problem you find interesting, you find an algorithm that you think will work really well on it, there you go. The other strategy is like an algorithm improvement thing, where you're like, I have a crossover that I think is a really good idea. And the trouble here, I'm going to warn you before I explain it. I think people think this is the easier of the 2 style projects, but I think you're wrong. I wouldn't say it's harder, I think it's just as difficult. I think where it gets easy is people think like, the methodology that I should follow to get my end result is more straightforward, but it's not easy, but it's more straightforward, maybe? Hard to explain. But if you say, I've got a crossover that I think is really good for this particular problem. So let's say you're looking at TSP, and TSP is good. So first of all, you have to ask the question, okay, if I'm doing something like, I want to find a new crossover or a new selection strategy or something. First of all, be aware that a good crossover might be good for TSP, but bad for N queens, but really good for graph coloring, right? Like it really depends on the problem. And even then, it's going to depend on the instance of the problem. Some TSP instances, one crossover might work really well, but another one might not, and vice versa. So it really all depends, but usually you would say, okay, look, I want to come up with a new crossover for TSP. You could say, I think I've created a really good general purpose crossover. Great, awesome. Just explore a couple different problems, fine. But if you're saying, I've got a new crossover idea for TSP, and you can't come to me being like, I'm going to do that, and here's my crossover idea, and it's like, what the hell are you talking about? It needs to be something that makes sense. Like, there needs to be an intuition as to why you're doing that crossover, why you've invented this new genetic operator, why you've invented this new selection strategy for this problem, and why it should be good. It doesn't need to be good, but there needs to be a good hypothesis to, like, a good starting point. You can't be like, my new crossover is you roll the dice and then you invert the number by the size of the population and then you do. Why would that work, right? Now, if you've got like an idea like, well, when you take the triangular distance of, assuming it follows the triangle property of Euclidean distance in the instance of TSP, and the distance of the curve is less than, like if you've got something like that, I'm like, okay, now we're talking. There's some intuition behind it, right? And it makes sense why it might work. So you've got your new genetic operator or selection or whatever. What you're going to do is you're going to use it and you're going to apply it to a suite of instances of TSP. And you need to show that it's better than kind of what we talked about already. Better than partially mapped crossover, cycle crossover, and order crossover. Those like 3 permutation crossovers we talked about. And you've got your new one. Well, what you're going to do is you're going to run your algorithm on each instance for each of the different crossovers. And then you're going to get the final results, and you're going to compare your results to the other 3. And if you come out on top, amazing. Chances are you're probably going to come out right in the middle, because everything always kind of works like that in evolutionary algorithms. And if you end up with coming up with something that always works, well, now we're talking. You found something really interesting. So that kind of gets to like, what would you even see like in a journal article? Well, usually it's either going to be a problem where it's like, that's a very interesting problem, and it's really interesting that you've applied something like an evolutionary algorithm to it to solve it, and you got better results than what other algorithms usually get. Or you've done like algorithm like enhancements where you're showing, here's a new idea, right? And you say, here's a new idea, and I'm showing you that it's good. You all should use this in your evolutionary algorithms. So those are like the 2 key ways to do it. Obviously, these aren't all the ways to do it. These are just the 2 major ways people usually do it. People who come up with bullshit genetic operators and do a whole analysis of it and submit it to a journal, they're going to be like, what the hell is this? That's a stupid idea. Why would you do that? We're not publishing that. But something that like made sense, like, it makes sense. And I want to be clear. At the end of the day, if your results are shit, it doesn't matter. Your grade is not dependent on your results. I want to make sure I'm clear on what I'm saying. If you did everything correctly, and you put in a good effort, you tried, and it came out shit, it doesn't matter, you can still get perfect. Now, if your results are shit because you did a shit job, well, you're going to get a shit mark, right? So I want to be, because people will be like, you said the results don't matter. I'm like, no, but your work was garbage, right? So I want to be clear on what I mean by that. So if you do everything right, you did nothing wrong, and in the end, it ends up being worse than random, which is hilarious, because you can never really be worse than random, right? Because you just take the inverse of what you got, and you're better than random. But if you get worse than random, then, but you did everything right, you can still get a thumbs up from me. right? You did nothing wrong. It's just, sometimes that's the way it goes. And we always kind of have to concede this when doing this type of work because these are such complex systems with so many variables and hyperparameters to tune and everything. It's just so complex. Solving problems we don't know what we're doing with. You just try. Anyways, if you haven't already, tell me if you're working with a partner and tell me if you're going to do a presentation. And if you haven't already, tell me what you want to do for your lecture because you need to start making those, thinking about those lectures. And don't tell me that, well, I haven't told you about the lecture. Those details have been on the course website already. You can go look at them. Even though they don't have deadlines yet, you can still look at them. Anyways, we're over time. I'll see you all later.